Head of the Intelligent Systems Engineering Groups at CSIR CMRI Durgapur. Besides his holds as the post of Assistant Professor in Academy of CSIR, the academic wings of the CSIR. He has obtained bachelor's degree in the field of mechanical engineering from NIT Durgapur, completed his PhD in the field of robotics thereafter. He has also obtained postgraduate diploma in design of mechanical equipment from the IEI India in 2006. Dr. Ray is working in the field of robotics for the last 2 decades and published nearly 60 papers in national and international journals and conferences. He has published a book on autonomous navigation of mobile robots using behavior-based robotics and machine learning technique. Till date, he has filed 3 patents and commercialized 3 sets of technologies to the industries. He is also a fellow of the IEI India, senior members of IEEE and member of Indian Science Congress Association for Computing Machinery, ACM USA. He has been awarded the prestigious IEEE India Council Award, Technologist of the Year 2023 by IEEE India Council, Engineer MP Bio National Award 2022 and Young Engineers Award in 2010. The vision of Dr. Ray is to solve various industrial and societal problems of the industries as well as the country through robotics, automation and mechanization, and thus moving the country one step ahead towards a developed nation. He dreams to develop more robots for solving the challenging problems in more domains to enhance the safety of workers, reduce drudgery, enhance production, environment monitoring, etc. for the betterment of the society and country. I would like to welcome Dr. Narayan Roy. The dais is all yours now.
Good morning. Good morning, dear participants. Professor Chakraj, a distinguished faculty member of BCREC Engineering College, and all other participants and faculty members from different engineering college, and also Professor Bawat, principal of BCREC. Thank you for this opportunity to introduce myself, and it's my pleasure to welcome you, address you in this session. Basically, the journey of robotics in India is very recent. But CMRI Durgapur started this journey in 1980s with the development of autonomous guided vehicles. This journey of robotics has been immense importance in the country. Your educational purpose. But initially, while beginning, obviously whenever you want to start a new thing or new course, there will be a huge resistance. So similar thing also happened in case of robotics, and if you can remember, similar thing happened in case of use of starting when in India computer was started or introduced. That time it was there. So the robotics is not or not against the human being. Robotics is for the humans. For example, probably you have seen the scenarios during the COVID period, where robots were deployed in the infectious wards for monitoring, for providing medicine and food, etc. So, robotics is, as I told you, not only for your to resist or to loosely or to harm the human, but it is for supporting the human worker or whoever is there, human operator. And another thing is that though we are working with robotics for a long time, say more than 40 years or 44 years, but still we are lagging. Because at the beginning, just I will show 2 videos from USA where the actual robotics are there. So let's start the first one. Basically, we are still in the era of secure robot, but nowadays. Just have a look with this video. So, can you identify the robots? Yeah, what is it? Louder. Drones. More specifically, we call quadrotor. Okay. So this video I got from Professor Vijay Kumar of University of Pennsylvania. This is cooperative robotics. Sometimes a number of people work together to achieve its goal, achieve the goal or objective or fulfill any mission. So here, all these quadcopters, quadrotors, they just play the James Bond title song. So all are autonomous. Another video, just I want to play, so which will give you the feel how robotics is being used for medical. This robot probably you might have seen some advertisements.
The Da Vinci surgical system is the most advanced platform for minimally invasive surgery available in the world today. The integration of high-resolution 3D vision, wristed instruments, and intuitive motion control enables the Da Vinci surgeon to transcend the limitations of conventional surgical technologies. making new, minimally invasive options possible for complex surgical procedures. Three network components comprise the Da Vinci surgical system: an ergonomic surgeon's console, a patient-side cart with 4 interactive robotic arms, and a high-definition 3D vision system. Seated at the console, the Da Vinci surgeon views a remarkably clear 3D image of the surgical field. The system scales, filters, and translates the movements of the surgeon's hands on the master controllers to 4 interactive robotic arms on the patient cart. The Da Vinci S HD system provides a magnified view, is a phenomenal immersive experience, are enabled by the computer processors of the system. These dedicated processors perform millions of safety checks over the course of a procedure for enhanced surgical precision and control. Da Vinci EndoWrist instruments are designed with a unique wristed architecture that provides 7 degrees of freedom for a range of motion greater than even the human wrist. This proprietary design enables surgical maneuvers impossible with conventional laparoscopic tools. It provides motion scaling that enables the surgeon.
So this robot is basically very well known. It is Da Vinci robot. Initially in India probably Apollo hospitals they were using it, and the telesurgery, this robot is basically for telesurgery with haptic feedback. Haptic feedback refers to that thing where you will get the real type of feeling when you are operating or when you are doing the procedure at the OT. So you will get some resistance or feedback while just using the scalpel or the knife, and that feeling will come to you through a feedback mechanism, and that is known as haptic device. So this robot is basically a tele-surgery robot where the doctor or the surgeon sits at one end, and this robot has 4 teleoperated arms with 7 degrees of freedom. So simultaneously you can see, you can think that 4 hands of a person is working on a particular procedure, and the doctor is the main controller or main supervisor who is monitoring this surgery. So telemedicine, we are very aware, mostly during this COVID period, telemedicine was very common. Now telesurgery yet come because of if there is network issue, there is communication loss, it is very dangerous. So still now telesurgery is not established in India in that sense, but it is working. It is somehow working in some of the hospitals, because only the reason robots doesn't get fatigue. So after one procedure or one surgery, the robot can be used, disinfect exercise, and then used for the next session without any rest or without any pause. But only the supervising doctors or supervising surgeon may be changed. So that is the advantage of using such a robotic device. And in the near future, when we will have a established network, established communication, and established and secure communication, that time we can use this robot for telesurgery at a remote location, say at a remote location of your Purulia or remote location of your Darjeeling area, and the main doctor is sitting somewhere in the heart of the capital, say at Kolkata or Delhi, and the whole surgery is being done by robotics. But these are we are to work there so that these days comes very fast and closer to this. With this, I start my presentation. I have just divided my whole lecture in two parts. First one, I will go how mobile robots develop, what are their principles, and what are various navigation techniques for mobile. And in the second part, I will show you how AI, or more specifically machine learning, has been implemented in one mobile robot for one exploration in an environment. So first part will deal with, say, some details of the mobile robots, and second part will deal something with the machine learning techniques for your. So this is the most important question. What is robot? The term robot came into the literature, or came into the picture in 1921 when a Czech drama writer he wrote one drama known RUR, Rossum's Universal Robot, where a robot was described as a servant of a particular person, and from that robot this term came to into the scenario. In Czech language, the term robot means work or do. Later on, there are multiple definitions came into the picture. It's a machine built for real world functions, that is computer control. A programmable multi-function manipulator, and then independently acting and self-controlling machine. So depending upon the country, so there are mostly few countries, say some country there are three countries. One is Robotic Institute of America, European Common Market, and Japanese Industrial Robot Association. According to them, the different definition is different. But initially, the term robot was meant for reprogrammable, multifunctional machine. For example, reprogrammable. Say, in the beginning of robotics, if you see, the beginning of robotics, you can see in 1916, when Henry Ford used this particular manipulator, which is nothing but a robotic arm, in his car assembly shop at Detroit. And from 1916, the concept was that a robot or a robotic arm can be used for different purposes. For example, say just like think of our hand, we can use it for gripping an object. We can use it for holding a water bottle. Even we can use it for holding an egg with very minimal pressure. And this same manipulator, in comparison, you can say the same manipulator can be used either for spraying, whenever in the car assembly shop, you can paint the whole vehicle. You can use the welding torch for welding any particular material or particular section. So this same robotic manipulator can be used for multiple purposes. Only you have to change the end effector, that is this portion, the wrist or this finger portion. In case of robotic manipulator or robotic arm is known as end effector. There may be gripper, there may be welding torch, there may be spraying gun. So only by changing of this particular end effector and reprogramming the whole functionality, the motion of the movement of the manipulator, you can use the same robot for different purpose. So robotic arm for the different multiple purpose. So initially, this was the concept where the robotic arm was used for multiple activities. And from 1916, the journey started. And now we are in the era of humanoid, mostly biped robot, humanoid, etc. And we have overcome a lot of journey through mobile robotics, through your bipedal robots, through your water robot, and finally reached the this humanoid robot. Still, journeys are going on. Where we will reach, it doesn't know anyone. And as I told you, the basic classification of mobile robots is just two sides. One is your robotic arm, when the initial beginning was started, and there are numbers of classification of this particular manipulator, robotic manipulator, which is also known as stationary robot, where they are depending on the coordination system, depending upon how they can be represented, either XYZ Cartesian, or you can define it as R, theta, phi, xi, etc., or spherical theta, phi, xi, and XYZ. So that way, representation and movement of the robot, based upon this representation and movement of the robot, it can be classified as stationary, and there are multiple sub-classification under this particular stationary robot. Cartesian, cylindrical, spherical, as I told you, serial manipulator, parallel manipulator, there are numbers of things are there. And another domain is not stationary, that is mobile. So mobile can be anything, either say some of us moves on two legs, human being. Say some animals they move on four legs. Some simply walk, just like cattle, they simply walk. Some horses, they trot, just like or trots or gallops. Some swims with their feet, and some of the animals they don't have any legs, feet, or wings. Still they move. For example, snake. For example, earthworm. They do not have any legs, feet, wings. Still they move by the reciprocity or by the contraction and expansion of their body parts. So that is, again, mobile robots can be classified into distinguished categories. One is your linked locomotion, just like legged robot, track robot, and wheel robot, and a combination of them, leg wheel, then leg track, wheel track. Those are hybrid robots. And another is linkless locomotion. You can see these two robots, serpentine robot and one spherical robot. They don't have any limb, that means leg, conventional limb, that's a leg, wheel or wing. They don't have, but still they move. So this serpentine robot, it has six, I will come to these robots later on. It has six segments, six small segments, and one segment moves in horizontal direction, another segment moves in vertical direction. As a result, there is a peculiar movement of, say, periodical movement, and it moves easily just like a snake. We have mimicked the movement of snake in this particular serpentine robot. Similarly, this spherical robot, it doesn't have any, as I told you, leg, wheel, track, wing, but still it is moving. We have implemented, pendulum. The pendulum is oscillating against a fixed point. Now, if you release the fixed point, what will happen? it will try to tilt the body or tilt the whole thing in opposite direction to that the pendulum bob is moving. So here we call it an inverted pendulum principle, where a mass is trying to move away from its the equilibrium position, and as a result the ball or the sphere starts moving. Without any leg wheel track, it starts moving. So this is the classification, and you will find multiple similar classification depending upon application and etc. This is just one example how we can classify the robots, mobile robots. And then the control. As I told you, there are two category of operation, means how to control the robot. One is autonomous mode, one is teleoperation mode. Basically, teleoperation mode may be either through a tether or cable umbilical cord, or it can be wirelessly. In some cases, the wireless communication may not work. For example, if the robot is moving inside a pipeline, a sealed pipeline from where your wireless communication cannot come out. In that case, due to your shielding effect or screening effect, there is no communication from the robot inside a iron pipeline and outside that particular pipeline. So in that case, either the robot must be autonomous, or you may have ether communication with the robot. So these autonomous robots are also the robots where the decision in case of teleoperation mode, the robot can be driven or can be operated from the outside by the operator. But when you don't know how in case of there is a long length of a pipeline, there is no question of giving a wire communication. In that case, autonomous navigation is better, and the whole decision of particular robot is programmed inside a controller. Either earlier people used to use microcontroller, nowadays people are using very small embedded single board computer inside the robot where the program is written. Again, this autonomy can be classified in two different modes. One, you can, if you know the environment of a particular area where the robot is going to operate, you can easily code how to control the robot. If else, through your logical sequence, if this happens, the robot should work like this way. If you know the environment of a particular area where is robot going to work, you can easily write the code. There is no issue, deterministic problem. But if you don't know the environment of the area where your robot is working, for example, we have already reached Moon, you know, but still we wish to reach Mars. Do you have any idea how the behavior will change in the Mars? It is never possible. But one thing is that we can understand the sensors which is mounted on the robot. For example, the eyes, wherever it goes, it will see the environment. Similarly, the camera, wherever you go, be it moon, be it underwater, be it Mars, it will take the picture of the environment and accordingly it will behave. So, in those cases, we program based upon the sensor feedback, means very micro level. rather than macro level, just a centralized control, we program in a very macro level, dealing with the output from the sensors only. So in case of Mars, you need not to worry how your robot should be programmed or how your robot should take decision. There you have to program according to the sensor's feedback. And that's why we need machine learning. Where the environment is known, your operations are very well known, you know what will happen in a particular environment, you can write a deterministic program. There is nothing to worry. But whenever you are sending a robot to a totally unknown environment, even the designer or programmer cannot think. So how to code there? And that's why this machine learning came into the picture. Where the robot will adapt its learning, just a human child learns. I will come to, in the second part, I will come how to accommodate this learning in robots. So basically, these two paradigms of autonomy are there. One is your deterministic programming, and another is this probabilistic programming or probabilistic robotics, where nothing is under your control. And as I told you, sorry for interruption, tea break is there. So let's have a cup of tea and join within 5 minutes, okay? Because I have lots of slides. Because this is a work for more than 20 years. So it's very difficult to deliver you within 2 hours. Still I will try to give you the glimpse and essence of the work, what we are doing and what the old work is doing. So let's have a tea break and then join within. So as I told you, programming of a mobile robot. But before that, you have to see how you can control a robot. Say there are two distinguished control schemes. One is our classical or deliberative control, and another is reactive control. For example, as a human being, your whole activity is controlled by a central system, your brain, and all these sensory information from eyes, ears, your skin, and every other organ organs, they are carried by your central nervous system. That is sensory feedback, sensory data are carried out by the main central nervous system and then sent to the brain for processing, and after processing the further action is sent to your motor nerve, what to do. So this scheme is classical one. Same thing has been adopted in case of robotics also, where the robot has a number of sensors. The data from the sensors are fed to a central control computer, where based upon your written code, some logics are there, and through that logic, a action is generated and then sent to the either wheel, track, etc. The issue is that you can see there is a sensor. The data from the sensor is acquired and they sent to particular world model. For example, when we are in this particular room, our eyes, it's a obviously stereo camera. It's not a mono camera. It's not a single camera. It's a stereo camera. It gets the image as well as depth information of this environment and make a approximate mathematical model of this whole environment. And then only we can work or we can work. Same thing is happening in case of robotics in classical control thing. Either it will have a camera or they with a depth information, say stereo camera, maybe stereo camera, or will have a laser sensor, ultrasonic sensor, which will give you the depth information of the surrounding of the environment. And from this particular data, a mathematics of the environment will be developed inside that particular computer. And then, after processing the sensory data, it will give the signal to the end effectors, maybe grippers, maybe wheel, maybe track, maybe leg, etc. So, you might have seen a human being, if you compare a human being and a robot with classical control, you will see that human is faster. Because our brain, there is crores of cells, they are processing the data. But in our robot, it is not yet so much. Means our processor is not so fast. It's based upon some gigahertz calculation, gigahertz computation. So that is a little bit slower than a computer, your human being. So this classical robotics or classical control is still slower. But if you see another domain, as I told you, so you have, in case of classical, you are getting the sensor data, you have a world model of the environment, mathematical model, where you feed the sensor data and you get a outcome from that, what to do, the action. And that is again passed to the motor. But in case of reactive, the world model, development of world model is parallel. It's not in series. So the data received from the sensor is immediately fed to the motor for decision. And parallelly, that same data is sent to the central control system for making a world model. For example, say the animal means insect world. Say ant is a peculiar insect or animal which we have mimicked several times. Still our optimization problems are based upon ant colony optimization. So these reactive behaviors are taken the example from this insect world. Say one ant, before that let's come to the human. Say as I told you, our brain is the central processing system. Say during your sleep, your central processing system is sleeping. Now that time, one mosquito is biting you. So what will you do? Does your brain process the information and send signals? Yes or no? No. Your brain is central processing system is that time sleeping. Then the central nervous system, basically the spinal cord, it acts. How? Whenever there is a sense, even if you are sleeping, your hand automatically goes there. Maybe target may miss, but this is done by the spinal cord, or means the central nervous system, not the brain. This scheme of this phenomenon has been translated to reactive architecture. For example, as I told you, ant, when one ant is moving inside one environment or one area, it does not make any mathematical model of the environment. It's never possible. Still, it moves in that particular environment and reaches the sugar cube, lying maybe at a distance from here to there. it will take, it may not be optimized, but still it can reach. So this control scheme is known as BIP scheme or behavior-based robotics, where the information or data from the sensor is processed parallelly to develop the world model as well as act immediately. So this lagging and being done in case of your humanoid robot or similar type of thing in comparison to human, it is lesser. You can see this spectrum speed of response is very fast and pretty fast, and there is no mathematical model of the environment. Prediction capability is very less, but there is other things also. But depending upon the environment, depending upon the operation of the robot or application of the robot, the control schemes are chosen accordingly. Where you must need a very precise movement of the robot, there we prefer to use classical control system architecture. But in other cases, we prefer to use reactive architecture if there is no such requirement of. And now come to the mobile robot navigation. This mobile robot navigation is nothing but answering three questions. What three questions are there? The first question is, where am I? First question of mobile robot navigation is, where am I? My position, localization. Say I am at the BCREC college. Then where to go? Second question, where to go? Say I have to go to city center. Then the third question, how? Then comes the question of path planning. So mobile robot navigation generally is the answer for 2-3 questions. Where am I? Where I have to go? And how? So these are self-localization, then path planning and map building and path planning. When my localization or current position is known and my goal or target position is known, I can make a map either through GPS or through laser data. So then I can make a path to go to my goal based upon the obstacle and available paths. So this is the nothing but the problem of navigation. And then this this navigation can be divided into three distinct categories. One is deterministic algorithm, then non-deterministic, and finally your evolutionary algorithm. And as I told you, this deterministic or classical algorithm, there are numbers of algorithms developed by different researchers over the time, and they are useful for different applications and different type of say time and processing and sensors they are required. So if I go, because this will take a long time, I will just go through the only the most important algorithms which are used in case of mobile remote navigation. These classical algorithms. This is a very well-known algorithm, you know, A-star algorithm. Probably some of you may know this thing, A-star algorithm. Okay, and this is nothing but a consequence of your previous one, where a cost is made, least cost is made, and you have to reach the goal depending upon your least cost path. And still these algorithms have different type of problems, because some of you may be from computer science background, some of you may be electronics, but mechanical people are there. So just without going into the mathematical details, I have just chopped out what is the method being used and what is their advantages and disadvantages, which is compelling us to use a different algorithm. Say, Easter algorithm has some and disadvantage. That's the depends upon the quality of heuristic. So it is not effective for the area where you need a faster response. So then again we have other algorithms, breadth-first search, where width-wise searching is done for getting the path and finding out the goal through that particular path. This is first one. Then depth-first search is there. Then probabilistic roadmap is there. These slides are available with the coordinator. You can collect that out. There is no issue. Okay. And also these all things are available on net also. If you wish to study, this potential field method. This potential field method is one of the interest of the robotics community. This is because this is very simple. Say it's nothing but depends upon the if you have this is a particular area. If there is no object, on the ground, say you can see the potential energy of that particular area is 0. So this is like this. But if there is an obstacle, so potential energy will be higher. And if you want to navigate from your start point to goal, you have to avoid the high potential energy areas. That means high potential energy areas are like this. So you have to avoid the particular area and you can reach the goal. So that's why this potential field method is always preferred, because this, as I told you, the obstacles are denoted with a higher potential energy and you will have a particular location. Say if this is my graph, so for a particular location you have x1, y1, its center point. And then if you draw just a approximated circle, you can get the area where the potential energy is higher. Similarly, x5, y5, x3, y3, where potential energies are higher. With you are just denoting it x1, y1, z1. Where z is very minimum or z is 0, you can use that particular path and you can reach the goal. So this is the simplest path planning algorithm robotics are using for navigation in any environment. And there are other algorithms, as I told you, rapidly exploring random trees. I am not going in details. Another is cell decomposition method. So these two algorithms, one is potential field method and another is this cell decomposition method. These are the popular algorithms we prefer to always use. As I told you, very simple to understand and very simple to code in the robot picture. So in this cell decomposition method, the whole area is divided in small cells, just like your grids in a particular room. So now you have to go from this particular point to that particular road. So this whole area you can divide in a smaller areas, and then you follow up. You can see, you can have a start point, and this you can follow this particular area. So there may be one obstacle. You follow up that particular area. then another area is there. These are basically some obstacles, and this is the whole area. Here is your start point and here is your goal. So you have to just follow this particular cell area so that you can start from this point to this point. Again, you get another area. You can follow this perimeter of that particular area or this area, and finally you can reach the goal. So cell decomposition is another way how this can be used, because here you have to follow the envelope or contour of a particular obstacle only, and you can reach from the start, from the goal easily. So this potential method and this particular cell decomposition methods are very popular, as I told you, and still there are obviously some limitations are there. Computational complexity is more in this case rather than your potential field. But as I told you, depending upon the sensor, what type of sensors we are using, depending upon applications, these type of algorithms, various algorithms are being developed, being used for different applications by different researchers. Then virtual impedance method. This is also based upon some attractive and repulsive forces. For example, how it is coding when there is a obstacle in this particular virtual method, virtual impedance method. In virtual impedance method, what is happening is the goal exerts an attractive force to the mobile robot. So the goal is just attracting the robot towards its destination, and wherever there is obstacles, it is creating some repulsive force. So these robots will be always away, these robots will always be away from the obstacles, which is exerting repulsive force. And the robots is moving only to the goal, which is exerting attractive forces. And in this case, this whole area of the navigation is divided in small segments, so that from I have to go from the 4 square areas, and then first one I will find where is a obstacle, obviously using my laser sensor, and it will exert an attractive, repulsive force. So the robot will avoid that particular location, and it will be away from that particular obstacle which is exerting repulsive force, and avoid and create a new path. So this way, there are various ways for calculation force, dynamic adjustment, and finally path planning. And this A-star algorithm, this variable impedance method, your cell decomposition method, all are your deterministic one. Means the mathematics are not probabilistic, where say 2 plus 2 will be always 4. But in case of this heuristic path planning, people are using this very well-known this machine learning or these artificial intelligence techniques, basically artificial neural network, and then fuzzy logic, and then generative algorithm techniques, and as I told you, there are other optimization algorithm also, and colony optimization, and then particle swarm optimization, and the recent one is bacterial following technique. So probably will be some speakers who will also teach these things. So I am not going into details of these things. But this basically artificial neural network, very well known technique to you. But initially when it was developed, we also implemented in some of the cases artificial neural network. We have a say one maybe you can say one is supervised, one is unsupervised. In case of supervised, I must have a teacher. I have a specific data set that is input data, and I have a particular goal. And if I have a trainer, I know to map the input data to output data very easily. But if there is no your trainer, that time it's a difficulty. But initially, when these other techniques, deep learning, reinforcement learning, when these techniques were not in the picture, we implemented this fuzzy algorithm and neural network. But in case of artificial neural network, just I am sharing, there is a huge problem. The problem is that basically we have faced in artificial neural network, say in one of our robot, it's an underwater robot, which was employed to find out the condition of a wall. If there is a submerged wall and you want to find out what is the condition. So initially we acquired a huge number of image data from the that particular image, and those input data were captured by a camera, underwater camera, and stored. They were processed and they were marked. Marked means, say I have an image, you know positive images and negative images, you may be aware. So in case of positive images, we find out this is the crack on the wall, and a portion of the wall there is no crack. That is my negative image. The positive image that there are various type of cracks, or the plaster has been removed, or some portion of the wall is damaged. So those images are my positive images I took in the training. And again, another set of images where the wall is perfect. Those images are negative images, and with those particular image data set, I make a particular input data set. Now, my trainer told that these are cracks, these are not cracks. And then, when I am giving the output, it was fine. Some data, some reading, we got very nicely. The algorithm worked fine. But sometimes we found that the prediction or the identification or detection is not accurate. So we investigated what's the problem. We saw that the input data, the illumination or the environment coloring, when we capture the input data, and the illumination, underwater illumination of that particular time, if it is different from its input data, there was a wrong result. That means if your environment illumination or environmental parameters, there is little bit change, artificial neural network failed to predict properly. So thereafter we implemented reinforcement learning, which is basically a unsupervised learning and adaptive in nature. So this artificial neural network, though initially when it came to the picture, we used it, but we faced a huge problem in this type of scenario where there is a change of environmental parameters. Okay, because it's not expected that one robot is developed for underwater inspection will give you a wrong result. So this artificial neural network may be useful for other works, but such type of detection, because this wall, underwater, this underwater wall work basically in your park, means Mumbai, where there is a chamber, inside chamber, where the nuclear fuel rod are kept. After it is used, it is kept there, and the thickness of that concrete wall has to be monitored properly. So that though the condition of the water, it is not normal water, it is D2O, heavy water, but still initially the image capture, environmental illumination was different, but later on when it was tested sometime in the evening, there is a little bit change in the environment and illumination, environmental illumination, and it gave a wrong result. So thereafter, from that onward, the robotics tried to find out a different type of approach, or you can say different algorithm, which will learn on its own without any trainer, based upon the data, and will give you a good result gradually, and it's like a human being. I'm coming to that. So these techniques, though this particle swarm optimization or ant colony optimization are still in the picture, but we are preparing nowadays these learning algorithms where there is a very less chance of mistake by the trainer. So obviously, and also some of the my post speakers, they will take care. So I am moving this way, and in case of you can say ant colony optimization, there is a concept of pheromone. That means one ant is moving, there is a typical chemical secretion from the ant which leads other ants to follow the path. So similar concept is also incorporated in the terms of mathematics in case of this ant colony optimization. So just, and as I told you this, I will come to more details of this navigation through artificial intelligence, because time, as I told you, time is very short. So as I told you, autonomy is very much required for industrial, for healthcare. Healthcare nowadays, you can easily understand that during COVID, these mobile robots were developed in deployed. Outside countries it was there. In India, few hospitals they deployed this robot, and they must be autonomous. Otherwise, it's not possible from move to one ward to another ward. And there are multiple applications where these robots are being used. And then your advantages is there. Autonomy is, you can say, human intervention is not required. Efficiency is very good, and even it can easily adapt to dynamic environments. And precision is also higher. But the main disadvantage is in case of autonomy is high initial cost. As I told you, the central processing computer must be of the most advanced feature, should have the advanced feature, so that it can process as fast as possible to give you the output in terms of microseconds, so that the response time is very fast. And obviously that computer will cost a high, and obviously whenever you are processing these algorithms on this particular computer, the time complexity, space complexity will obviously be higher. You have to take a consideration that these complexity are there, and energy consumption is high, and also whenever you are using autonomous robots, these ethics and legal concerns are there. So still nowadays in Indian scenario we prefer to use teleoperated system. And coming to some of the examples where we are using teleoperated robots. Autonomous robots are okay, but still because some malfunctions may happen. Even if you are using a high-class computer, you have just 2 months back there was a blue screen scheme. You know, from Microsoft there was a issue blue screen case. So we can do nothing. And if this robot is a window-based system, such type of bug, at that time the robot may malfunction. And from that malfunction, there may lead to an accident. Though a variety of robots nowadays are being programmed in Linux-based system, but still some robots are there, with some, not some, more, a significant amount of robots are there which uses your Windows system. So in such cases, if the OS malfunctions or some program malfunctions, the autonomy of the robot may hamper and it may be dangerous for human being. So though we are developing autonomous robots, still there is the provision for manual override. Means whenever human wants, it can do. Maybe 2-3 robots are moving and one operator is operating or just supervising the action of the robot. But autonomy is there, still this teleoperated is preferred. Number one. Number two is that for autonomous robots, environment must be structured, mostly structured, and in some cases in outdoor environments there is fine, there is no issue of any malfunction. But in case of indoor applications, autonomous robots are still to be taken care, and the environment must be structured. So these various types of navigation, as I told you, and mobile robot systems we have developed. This is a first generation robot that was developed for your outdoor exploration. This is a track robot, and gradually this robot was developed from all Indian components. Mostly these motors, nowadays the motors are being used, iron core. The motors are developed with iron core. But some of the motors nowadays, they are using rare earth material core, making the motor very compact one. And it obviously it's costlier. The robots which you see outside India or in Western countries, most of those robots, they are using rare earth material core, not iron, soft iron core. They are using this type of core. As a result, these motors are very costly. And this is a first generation robot developed in 2003-4. This robot is known as alternate mobile robot, and obviously stair climbing capability and other things are there. This particular obstacle avoidance is required everywhere. As I told you, obstacle avoidance is required. Then the initial version was developed from very crude components, indigenous component, lead acid battery, and then your Indian motors. But later on, the lead acid battery was replaced by lithium ion battery. This robot has been developed in 2005, and these lead acid batteries were replaced, and as a result, a huge weight of the robot was reduced to a significant value was there. And the motors we have used in the second version, it was, as I told you, rare earth core motor, nowadays available in India. And the sensor, you can see that particular blue part, it's a laser sensor which will give you the particular distance or of a particular obstacle, and you can make the environment accordingly. And a series of development, because when you are entering the domain of mobile robots, with the passing of time and advancement of technologies, you have to follow that particular path. As I told you, initially we used say lead acid battery, then we used lithium ion, then lithium polymer, and nickel cadmium. So that way we are going following that particular path as per the international standard or international works being carried out. So this is the another version of robot. This particular robotics transformer, as I told you, hybrid robot. So this is a, you can see this is a hybrid robot. The same robot either can be wheeled or can be tracked. Here the change has to be done manually. I will come to another robot which is interchangeable, means wheel and tracks are simultaneously there. It changes automatically. But here you have to change the track and wheel depending upon your requirement. Because track robots are useful for sandy area or very loose where there is loose soil. And wheel robots are very useful on the plain land. In case of say grass, in case of road, this type of track wheel robots are useful. So another is that as like a human being, these robots have a definite front and back. So it can move in forward direction, it can move in reverse direction. But some robots are there which have to or which has to move in any direction. A typical type of robot is there. This particular robot can move in any direction. We have sensors in 8 directions, and the robot can move in any of these 8 directions. It's known as omnidirectional robot. Then these are mostly this is as I was telling, this is a robot, basically a hybrid robot. A wheel plus track, both are there. So whenever it is moving on very undulated terrains, this robot will use its track beds. So for example, it is overcoming, you can see it's overcoming your stairs. In that case, the robot will automatically change its configuration from wheel to track, and it cross the stair, and again when it reaches the plain land, it will come to the wheel. Because when the robot moves on wheel, it is very faster. But when it is moving on track, it's basically to avoid loose sand or loose soil or pebbles or stones are there, that kind of track rails are there. So just let me show, I have one video with this one. And the configuration can be changed accordingly whenever whatever you require. So this is one stair climber robot. So similar type of robots are there. When you reach the mirror, you can see. Now, as Professor Pawar was telling, robots are basically for industrial application. This is one mobile robot. This is a amphibian robot. That means it can move either on water, or it can also move on the surface. And obviously, this robot has been developed to cater the need of industry, basically coal mine. Probably some of you may know there was one disaster, one accident in Mojave, Korea in 1990s, where the water in the underground mine tunnel was there. Because the miners who were working, they wrongly hit on a particular wall, where on the other side water body was there, and the water suddenly entered in that mine tunnel, and it was flat. It was a flat. But it is very difficult to find out if that particular human miner are there and trapped. And though they may be at a safer location, but it is very difficult to find out their location, because a part of the mine tunnel is filled up with water. Because these tunnels are not on a particular plane, they are in an incline. Say there may be some incline, and the disaster happened at a particular location which is at a lower level. So water is there at the lower level of the tunnel, but on the higher side, or the elevated height, the water is not there. The miner may be trapped there. It is very difficult to locate. So this mobile robot was developed with it can move in dry mine tunnel as well as under water also, so that if someone is trapped on the other side of the flooded tunnel, you can easily reach. Though we call it a subterranean robot. Just let me show one video how it and all these robots are basically to solve the problem design from this scratch. It is not that we buy a robot and start programming. It is never possible. Depending upon the problem, we have to design the robot. That is mechanical, then electrical, then electronics, and finally your hardware. You have to do. This is the robot. In this video, you can see how state-wise development is done, and video is not working. So initial, after developing the mechanical chassis, then all the electrical components are then integrated with it, and then finally electronics are there, integrated sensor, and finally your control software is written. And then a series of laboratory testing are to be done. Basically, this is the already bare robot. Then there is thruster. You can see these blue ones are thruster only for moving on the water, surface of the water. And then there are drag wheels also. And sometimes, as per the requirement, and we have a different underwater test facility where we trial the robot in the laboratory for continuously, so that you can easily find out how the deviations are there. Basically, once you integrate all the or assemble all the sensors, say your motor or thruster, because in any robot, one motor rotates in clockwise direction, the other motor rotates in anti-clockwise direction. So for a particular voltage, the characteristic in clockwise direction in an anti-clockwise direction may be different. Means this characteristic is different. So if you are asking the robot to move forward, there may be slight deviation. That's why a multiple testing is required. Both if it is a land-based robot in land, if it is a water-based robot in water, you must tune both the motors or thrusters, so that if you want the robot to move in straight line, it should move in perfect straight line. So thereafter, there are multiple testings are there, and finally, as I told you, the robots are for industry, and this is one underground mine under BCREC, Satgram Fourier. It's just on the way to Asansol, and the following below graph is showing this green was our desired path. This is our desired path, but you know, when the robot is moving, there are lots of slip friction are there, so it cannot move in a perfect straight line. But still, with its input of data, means it has some odometer, it has some radar sensor. With those data, the robot is constantly trying to follow that path. Means you given a straight line path to follow, and robot, in spite of its slip and friction, it will try. Then this is as I told you, it's a amphibian robot. This is a planet gallery. This is a fully planet gallery, and underground mine there is no line. So this film has been shot using the Kaplan, which is worked by all the operators. And this blue one, this is nothing but the sonar. There is a one sensor, we call it this is a sonar data, sound navigation and ranging. This is an underwater sensor which uses sound, principle of sound to detect obstacles. And you can find, as I told you, there is a the tunnel where we tested, it was a elbow-shaped tunnel. So if you let the robot go along that particular tunnel, and if it reaches on the other side, and there is an underwater camera also, you can find out it track miners there. And these mine people, they have a map of that particular tunnel. So you can easily identify from this type of configuration which tunnel has been flooded and where the miners are trapped. So from that particular location, you can make a borehole from the top, and you can say your support, means life support, oxygen and food that particular location. So this is a solution to a particular industry. Similarly, as I told you, this is a spherical robot using this particular inverted pendulum principle. This is also other robot. So this will be, you can I can demonstrate you later in the laboratory. And this is another problem solved for Ministry of Coal, means Coal India. These mine tunnels, underground mine tunnels, they have two defined problems. One is the presence of methane gas. You know, in underground mine, there is a chance of explosion and due to that methane gas. And this is one problem. Another problem is that there is always a chance of root collapse. As I told you, the roots are supported. When the coal is extracted, there is a hole, a void is there. And when there is a void, they use, say you can say wooden pillars to support this root. But sometimes there is always some depression in the roof or wall. And you have to identify that, because your miners are sent to work in that particular tunnel. You must know whether there is any gas is there, or whether any of your there is a chance of root collapse or not. So this robot was developed with funding from there, and this has been tested at another colliery at PCL, colliery, where you can find this particular robot has been tested over a length of 50 meter. Means you are at a distance of 50 meter at a safe location, and you send the robot to get the information of a particular zone, whether there is any methane gas or not. And all the data are transmitted remotely to the base station. This will also be demonstrated, and these are some of the pictures. This is another robot. As I told you, robots are for helping the human operators or industries. If mechanical people are there or know about a boiler, the boiler is one of the essential component of any thermal power plant, where high pressure, high temperature steam is separated, and the high pressure, high temperature steam is sent to the turbine, and the water, associated water, is again sent to the boiler for reheating. So this particular component, this boiler header, is nothing but a very thick, say 2 inch to 3 inch thick pipe with both ends sealed. There is no chance of leakage. But as this particular header is under high temperature, high pressure, there is always chance of cracks, and there is scale formation. And if you didn't notice those cracks, there is a accident. Either may this header may be blast, and the power there will be power stations shut down. And this shutdown, one such shutdown of a say 500 megawatt power plant costs around 4 crore per day. So that's why all these power plants, they take annual shutdown, maybe twice, once in a 2 year or once in every year if it is very old. And during that particular shutdown, these headers, boiler headers are inspected. How? Earlier, they used to use, endoscopy. Endoscopy is done by a very specific camera. It's nothing but a say 8 to 10 mm diameter wire with a camera at the tip. So it's it is known as boroscope. But that boroscope is nothing but a cable with a camera and LED illumination at the front. But the boiler headers, they have, you can see, boiler headers have this type of holes. These holes are connected to these holes are connected with the water wall tubes going to the boiler. Now, if you are passing a flexible wire through this, what will happen? After going to some distance, the tip of that particular wire, which is nothing but the camera, may go inside, may get entrapped in these holes. So if these headers are say for 20 meter, it's very difficult to inspect. So NTPC approached us for developing such a robot, and as I told you, this particular robot was developed due to times, and I am not going to describe. It has used the principle of just like snake. The main challenge was there in the boiler header. You have the boiler header, the dimension of the boiler header inside diameter is around 250 mm, 250 to 550 mm. It's a variable diameter. But the inspection hole through which the robot should enter, it's only 75 to 90 mm. So you can see it's around 7 to 8 times. So a robot will insert through a hole and then it should expand. So you have seen snakes, it's go through a hole and it can then erase its wound. Similar concept has been adopted in this particular robot, where just look at the principle how it expands, because so initially the diameter of the whole system was 70 mm. Now as it gets expanded, it can reach up to 350 mm. And this is a camera. This camera has been backed up with image processing techniques, so that whenever some abnormalities are there inside the header, it can be easily pointed out. Basically, the cracks, basically the scales or any rusting type of things, if are there, it will be automatically detected out through a conventional image processing technique adopted there. And as I told you, here we have faced a very big challenge for wireless communication. The wireless communication fully failed because of this type of iron pipe. So we have to go nothing but this wire communication, through which we have power. And this is the GUI, means graphical user interface, from where you can find out. This is in one of the NTPC plant that we have. This is inside the header. You can see there is a foreign bodies, and that is identified in the processed image also. So this way robotics is being used for various industrial and societal application. So I am not going so much in this thing. Let me start the next session. So mobile robots are developed based upon the need and where is the application. So the robot may differ from one to another. Means a same robot cannot be used for one application, developed for one application, it cannot be used for a different application. It's not always possible. And now, as I told you, the conventional navigation sometimes fails, where the information about the environment is not known to the programmer. So how to deal? So mobile robots, some of the mobile robots are used for, you can say, autonomous surveillance, where human operators may not be present. For example, some of the areas you can see, this is a area, NTPC has a plant at, you can say, Rajasthan, and the temperature range is around 46 to 48 degrees centigrade, and you can see the area 14,000 acres. Is it possible to human to have a surveillance and monitor all the solar panels installed there? It is never possible. So surveillance, autonomous navigation is required for such type of robots. Another is that one floating solar panel at Telangana, and the area is also, this is also on a water body, on a large lake. It is very difficult for a particular human to ride on a boat and inspect regularly, so it is not possible. So these for these two particular areas, we are trying to develop two mobile robots for autonomous exploration and autonomous surveillance. And commercial robots available outside India. These are say security surveillance robots. Then these are power plant or substation surveillance robots. And this you also know. This is a very well-known robot of Boston Dynamics. And these, their surveillance are required, and for this autonomous navigation it must. And as I told you, mobile robots have a number of sensors with it, starting from infrared sensors, ultrasonic sensors, lidar. Obviously, depending upon your cost, depending upon your application, there may be 2-3 sensors. All the sensors may not be available on a single robot because it's a very, say, radar sensors, then your stereo camera, these are very costly, even this thermal camera. So depending upon your application, 2-3 sensors are there. Just like in our case, whenever we hear a sound, first our ear hears that sound. Then our eyes are attracted to that sound. That means, but for a locating one object, the interference or say interaction or collaboration of two sensors is required. And this is very commonly known in robotics as sensor data fusion. The data from two sensors at least are required to establish the presence of obstacle, or the safe navigation of a mobile robot. And as I told you, autonomy, as I have discussed. And the initial stage of autonomy was started in 1956. There was one AI.com conference, and there was one Professor Marvin Minsky, who coined out this artificial intelligence term. And from then on, this is a timeline how this artificial intelligence and other robotics, other robots have been developed. During that time, a very good example was there how AI was coded in a very nicely with, as I told you, without using any computational platform, high computational platform. This image shows a picture of it. It is known as gray water stopwise. It's a fully automated robot developed around 1960s, 70s. This principle of this robot is that it has a solar panel. And means solar panel, that means that time it was not a solar panel, it was a photodiodes. And it has some motor. Okay. So whenever the robot gets solar sunlight, it starts moving. Whenever there is very less light, the motion of the robot is very slower. Whenever there is dark, the robot doesn't move. So this way, the environmental stimuli that's in here, it's the light, has been used to drive a robot autonomously. So this is the first development of first autonomous robot. Gradually, days passes on, and numbers of other researchers also they try. This is another vehicle developed later on. And finally, these robots, these are known as photophilic robot, means it loves sunlight. Why? Because if it gets sunlight, later on people has developed, if it gets the sunlight, its battery will be charged. That means the sunlight is giving food to that particular robot. So it will go near the sunlight, and wherever is there dark, it will start move away from the robot. This way, the means nature's principle has been mimicked in various robotic systems. So this I have already discussed. Now let's come to some of the architectures how this artificial intelligence can be coded in a mobile robot. As already I have told you regarding this behavior-based robotics, still there are some leaders which has developed a different mix. These architectures have been developed by this Professor Rodney Brooks, senior professor from MIT. So 1986 he used this particular scheme. How? Let me give you one example. This is the architecture. Say one robot is moving in a particular road, autonomous robot. Now its goal is to reach from location A to location B. Okay. So from location A, going from say from BCREC to city center, what will be your first consideration? Tell me. What will be your first consideration? You want to go from say location A to location B. Say by walking yourself. Means
What is route?
yes. Next.
Next is the other way is the route.
That will come later on. The first question is that whether you have food in your stomach or not. So, if the robot has enough charge or that energy to fulfill its mission, it will then only take the mission. Otherwise, such surveillance robot will be lost. Please be seated. if you are going to such a 14,000 acre area with robot hardly charged or there is no charge, your robot is gone. So the first question is that you must be fully charged. Means your stomach should be full. Next one is that your what is your goal? So you will find the goal and you will start moving. But before that, the first consideration means first preference is that I must be fully charged. Then second one is that I want to go to say particular location. I through a path. I have to overcome obstacle. I will reach the goal. But if I have stuck with the obstacle, you cannot reach the goal. So second consideration. First one is your this food. Second one is your follow the path. Say this is a highest priority level is start. So you are following the path. There are obstacles. Now there are multiple obstacles. You cannot come out of that particular obstacle. So it's also an emergency layer. Means emergency situation. You have stuck inside the room. Say, while you are moving to a particular goal, you have stuck in a jam. So you have to find out the way how to move away from that particular stuck position. So these are the emergency layers you have to take in consideration, and these are as per preference. First preference is your how much energy you have. Second is whether you are stuck in obstacles or not. Third one is follow. If all these parameters are okay, means you have enough charge, there is no obstacle, then only you can roam or wander in a particular area. So that's why you can see first one is the emergency layer. Are you struck? If not, then the next priority, if you are not struck, you have to first consider that. If it is okay, then you go for follow the target. If these two are okay, then this is the motion layer. So this is a architecture. This has been copied from ant, how they are moving, and this is subjunction architecture often used for implementing AI. Similar algorithm, similar scheme has also been developed. This is known as motor schema. This is mimicking human schema in the brain. Now come to learning. Why we require? As I told you, the environment is not known to you, and the programmer cannot even imagine what will happen. So in that case, learning, implementation of learning in robots are very much essential. So there are three different types: supervised learning, unsupervised learning, and reinforcement learning. In first two sets, data is required. In the third one, you need not have any data. As I told you, extra planetary exploration. There is you cannot get the data from the Mars. So that's why this algorithm is preferred. How it is working? It is working based upon the interaction with the environment. For example, say a small child is there and one candle is burning. So now, if that particular child sees that flame of the candle, what will he do? Can anybody tell? Say, yes, he will try to catch the flame. But once he touch the flame and get the burning sensation, will he or she do it in his or her life second time? No. Why? This is the punishment he has got. And this learning will embed in his or her brain for throughout the life. This is reinforcement learning. So similar concepts are being incorporated in mobile robots also. Basically, this reinforcement learning, they can be developed in a can be solved in three particular way. One is dynamic problem programming, another is Monte Carlo simulation, another is temporal different algorithm. I will just discuss how we have implemented this Q learning of policy TD. Of policy means there is no definite policy for this particular solving this particular algorithm. That's why it is known as offline. And let me give you the example so that you can understand easily. And as I told you, in most of our robots, where we want to do very faster processing response, the whole control is divided in a multi-agent system, where, for example, how multi-agent system works. Say if you have used, say, very old computer, say Windows 95, that time we used to use PS2 mouse or PS2 keyboard. Now, if that time you take out the PS2 mouse or keyboard, what would happen? The computer used to get hang. Then we have to again restart it. But now it never happens. Why? Because there is a peripheral agent who constantly monitors all the peripherals. Say whenever you are inserting one USB mouse, USB camera, it automatically detects the new hardware and it starts installing the driver. So there is one agent who continuously doing this thing. So this is a multi-agent concept in robotics also. Say we do parallel processing so that the monopoly of a centralized system is no more there. And now let us see how we have implemented this multi-agent architecture and reinforcement learning in a mobile robot. So, say I have a robot. The aim of this robot. Let me go directly to the example. I have a particular robot. This robot is having three sensors. What are the three sensors? One is, as I told you, these are the three sensors the robot is having. One is the battery level detector, and another is the light sensor, which is defining as the goal, and another is the ultrasonic sensor to avoid obstacle. Now, one robot is there in the environment. You have a goal at the end. You want to reach that location avoiding all the obstacles. You don't have any deterministic algorithm with you. You don't have any data, so you cannot do any algorithm programming or any fuzzy set. You have to reach the goal. Now, how we are doing? So these sensors, as I told, these sensors are defined as agent. Each sensor is defined as an agent. Say I may have say agent 1 for light sensor, agent 2 for ultrasonic sensor, or that is more clearly obstacle avoidance agent, and another is your battery level detector. Three agents are there. Those agents are constantly acquiring the data from the sensors when the robot is moving in a particular environment. So multi-agents are there always. So this is a scheme, and then As I told you, in everywhere, people, say 3 people are working, 4 people are working, there must be some mode of collaboration, mode of say prioritization. Obviously, in case say for example in your department, the HOD is the person with the highest priority. Then the deputy HOD of the next senior most person, he will have the second priority. Then and so on. So this type of priority are also given to agents. As I told you, if you want to move from BCREC to city center, there are 3 things we are going to consider. First one is whether I am hungry. That means your battery level detector will check whether you have enough energy or not. And mathematically we can define that those 2 states, either yes or no. Okay, so battery level detector will have only 2 states, fully charged or no. So yes or no. Similarly, your light sensor, your aim is to find out the most illuminated part of a particular environment. Say for a room, here only say one light is on, other lights are off. So light is most there. So if a robot is there with having a light sensor on it, how the environment will look? Okay, say a robot is there and only one light is switched on. So this is the situation. Okay, and the light sensor will give you that the most intense zone is here. Second one is this, third one this, and so on. And we call it a perception. Just like human, we have a percept with the environment. So perception 1, that means my goal is to find out the maximum intense zone of a room. So the maximum intense zone is, then we have divided the 360-degree surrounding robot in 8 sectors. Okay, 45 degree each. And we have measured the intensity of the light using light sensor, and this is the maximum one. So the maximum intensity grid is 0. Then second one is 1, second one is 3. And so I am considering only 3 consecutive maximum zones where the light is maximum. Now the thing is that sometimes it may happen the robot is not at all moving. You are getting the same data all the time. Is it possible, alright? Sometimes it is possible that the robot is stationary, it is not at all moving, and you are getting the data, same data continuously. But it is not desired one. So you have to check whether my last data or last consecutive 5 data are same or not. Then only you will understand, yes, this robot is moving. If your 5 consecutive data are not same, I have another perception. The robot is moving. So the data from the sensor, or you can say the goal seeking agent, it will give you 4 data. 3 data are 3 maximum intense zone of the environment, and last one is whether the 5 data are same or not. You can reduce it also, 3, 2, etc. Next one is that once you have defined your goal, you can find out the obstacles. You have to move to the goal. Now you have to find out your safe path. Now, if the robot is looking like this, and if a robot has a ultrasonic sensor over it will see 360 degree around the robot. And you can, if you are scanning 360 degree, then again there are sectors, 7 sectors are there, and you will have very close. Say, if you can think of a circle very close to the robot, which is say less than 50 centimeter, if there is any obstacle or not. Second one is 50 to 100 centimeter, whether there is obstacle or not. Then 100 to 150, another circle. Then beyond 200 centimeter, whether there are obstacles or not. So your first aim is that you have identified 3 intense zones through which you have to move. Then you are finding whether there is obstacle or not. So this data you have got, and when you fuse this data, there are 3 things. As I told you, there are here in this case we have taken only 3 things. This is, say, my battery level is full. That is, I can make my mission, so it is 0. Then, as I told you, 3 maximum data, 3 maximum intense zone of a particular environment, and this is repeated or not, means 5 data, 5 readings are repeated or not. And then again, obstacle, why is the obstacle? So this particular table defines the state of a robot. That just means the localization of this robot, in which condition the robot is there. Just like any human being, similarly this robot can be defined based upon the sensory data, and this is known as state. State of a robot. If a robot is here and you have mapped all the environmental parameters by the sensors, that can be defined by the state of the robot. Now, based upon this state, going through your sensors, we have different action. Say you go to this particular slide. Now you see this particular zone is has the maximum intensity, and your aim is to find out the maximum intense zone in the environment. It may be different also. If you are using a GPS, that will be a different configuration. Your robot should move in this direction. It is your goal. So, what will be the action? So, the robot is moving in facing in this direction. Now, your robot should move in this direction. So, if your location is your intense zone is 0, so you need you require the robot should not take any rotation. But if it is 1, so 45 degree apart. See, if it is 45 degree, then if it is 90, then if it is 135, and corresponding. First one is 0, means 45 into 0. Then in this direction, if the intensity is in this direction, then it is 45 into 1. Then it is 90, 135. Similarly, means the robot will provide a rotation. Now, this is only the rotation. Now, the motion of the robot. 1, 2, 3. These zones are the maximum intense zone. See here. If I consider now, this is, say, these are the circle. Now, say in this particular zone there is an obstacle. So if in case of zone 1, if there is an obstacle within 50 centimeter, is it possible for the robot to move? Because there is a chance of collision. So whenever there is obstacle very close to robot within the first circle, or we have denoted as 0, there is the movement of the robot will be 0. When there is action is 0, the robot either should not move or move very slowly. So that time the RPM of the motor should be 34. If the obstacle is in the second circle, you can see, if the obstacle is in the second circle, the speed will be little bit more. If the obstacle in the third circle here, so the speed will be little bit more. So direction is giving in from this particular goal seeking agent, and the motion of the system will be given by the obstacle avoidance agent, and this is the action correspond to a particular state. Now the robot must have two actions, one is rotation and another is straight line motion, velocity. Then only the robot can reach the goal. And as I told you, you have 3 different sensors. From that sensor data, you can know what is the state of that robot, whether illuminated fully or not. And this is the state action table. In one side, this full table is S state, and as I told you, action is a little bit different. Action have to be chosen. So this state action table, there are multiple cells. These cells you can filter initially, as I told you. In reinforcement learning, we don't need any data. So no data. You can filter all these cells with 0 or uniform number or any random number. This cell can be filled up. And when this robot, say, having a particular state S2, say at a time t, S2 state is there. Accordingly, obviously, what is our aim? Our aim is always to maximize our own gain, profit. So, if I have that particular state, your action will be that corresponding to particular one, that action whose Q value is higher. If it is 0, it will take random values. If it is any other random value corresponding to S2, it will be a particular value. And whenever at a time t, the robot is denoted as at a state S2, and it is executing, say, any action, the robot will move from one location to another location. And in the second location, what will happen? Either your goal was to find out the maximum intense zone. The goal is that whether you will find that whether your illumination or your that particular light sensor have reached a higher value or not. Means your aim is to reach the maximum intense zone. You have started from a lower intense zone. Next move should be such that the intensity is higher. If not, your last action should be punished. So this is the guiding equation where you will receive one reward if your previous state was inferior than the current one. You will receive a reward. But if it is opposite, that means your last state was higher one, you will be punished. And this punishment is done in such a way the value is very high. And as I told you must keep some reward if your last movement was very good. If not, you will be punished. And in that case, this value of R will be so high that your table, this particular Q value will be negative. And corresponding to say for S2, you have executed one action, and if you are rewarded, your value will be higher. Every time for this particular step, this action will be chosen automatically. If not rewarded, this value will be huge minus value, say minus 10,000, minus 1 lakh value will value will be there, and this action will be never chosen in consequence movement. So robot will not adopt this motion. As a result, this way robot will select, as I told you, this is the priority wise agent prioritization of the agent. Agent 1 is the topmost priority, will have. Agent 2 is second one, goal seeking, and then obstacle avoidance. And there is a modifier, means which action to take. So accordingly, this way goes on. This, as I told you, first one, if there is a this value is 0, this second agent is taken care of. Then either if this particular zone is most means having the maximum intensity, so it will have 6 into 45. Then in the first, if there is obstacle in the first location, the robot will take no movement. But if there is obstacle in the second one, the robot will take the RPM will be this way. So, and using this logic, the robot starts moving towards its goal. And these are this representation of the case means both the agents should have a common space, means whenever 3-4 people are working, we take decision based upon our common area of interest. Means all of us should agree to a particular decision. That is common space sharing. Then only the robot starts moving. Similar principle have been adopted here, so that whenever both the agents are conforming to a particular motion, the robot starts moving. And there are various this mathematical formulation. These are have been used in this particular thing, and obviously initially this algorithm has been established through MATLAB simulation. And this is as I told you, initially the state action table for a particular, say, light seeking agent, I have filled the whole Q table by random value, and it looks like this. Whenever the robot is moving from here to here, you can find out the refined values. Means for a particular action state of the robot, the actions are already defined. Means for S1, only particular action will be chosen. Similarly, this is also for other agents also, and these are the various robotic systems that has been used to implement these robots, and various type of environments. As I told you, artificial neural network has a deficiency of this type of environmental illumination or parameters to check whether this system works in all the environments, different type of environments, in daytime, in indoor, outdoor, in day and night, we have experimented. And before going to this, various lots of experiments have been done to implement the algorithms. And let me show. Finally, for example, when we are doing one work, if it is the work is the 41st, we are doing it the 41st time, there will be large mistakes, number of mistakes, and our learning will be more. As days pass on, if we are doing the same work, the learning means rate of learning or updation will be very lower. So initially when I started the robot to move on a particular direction, the number of updates was very high. As it passes on, number of runs is increased, it is having a saturated trend, means there is no learning at all. That means the robot has learned. So when initially the robot was at this position and reached that location, say it has a 1000 iteration. But when second time, third time, fourth time, fifth time, after fifth run, I found the iteration has reduced it very minimum, and the response time of the robot has increased. So these are the number of updates in the queue table when initial first run was there, and as gradually times pass on, this means fixed. And there are some rules how, or some theorems how you can prove the concept of learning. So there are some methods, convergence of the queue values, number of policy change, by which you can understand this how the robots whether have learned or not. As I told you, this is the data from the final phase. Initial the queue table was like this, but at the final value, it with reference to state, particular state, the action is already defined. Initially here multiple values were there, but here for a particular state only one action is there. So this table converts to this way. And I am not going into more details. Also, as I was telling about you surveillance, this computer vision is very much required. Where this reinforcement learning, another form, deep learning, that has been gradually being implemented. Because until and unless the environment is visible to the robot, in some cases we are using laser sensors, but in some cases we are using cameras. But in those cases, if the environment is not visible, this navigation using this vision base is not possible. So we are also working with this type of application of this deep learning, where these visions are computer visions are being implemented for movement of the easy movement of the robots, and that way human surveillance are going on also. Just with this, I will end up just a small video of that particular. This is the robot, as I told you. This is the robot. This is basically a Lego-based Lego Mindstar robot. We have used a light sensor and a ultrasonic sensors on the rotating head, so that you can scan 360 degree around the robot. And from this particular video, you can find out how the robot is moving towards a light source. Here in outside is sun was there, and some obstacle was placed, artificial obstacle. You can see sun is in this direction. The robot is autonomously trying to move in that particular direction. It's when it is just the whole sensor head is rotating, it's gathering the data, that particular data, and it's moving in this direction. Obviously, avoiding obstacles. So it's a fully autonomous robot, and it's similar. The experiment has also been carried out in night also. It's not visible. Yeah, the robot was placed in a dark cell. Now the sun was like this. So this way, our reinforcement learning, or more specifically this Q learning, has been implemented in for autonomous navigation. This is a platform, the experimental platform where we have implemented this thing. And now the platform has been already changed for because that time this is around 2010. So nowadays this technology has been upgraded and a higher computational platform is available. That time it was not there. We used a laptop as the processing unit, and the data from this particular robot used to transmit to that particular laptop through Bluetooth, and after processing the actual action to be taken, the robot has to undergo has been passed on to this particular robot to act upon. So this way, this robotics is going on. And thank you very much for your presence hearing, because these works are carried out for last 20-24 years. It's not possible to feed you even with this machine learning. These took around 4 to 5 years for implementation and getting the data. This work has been carried out around 2010, when in India no machine learning, this term was not there in India. So that time it was very difficult, and that thing has been implemented in mobile robots, means applied. The theoretical code has been transformed to a applied one and then used it. So within means 1 hour, half an hour, it's very difficult to take. Still, the essence of machine learning, reinforcement learning, how it is being coded for data-less, means no data, still robot is moving or system is moving. This work is just, I try to give you some essence. So if you feel interested, you can join CMERI, you can visit CMERI. And I also request the faculty members and students to have a collaboration, because researching, though the terms robotics, machine learning sounds a big, but still we are not getting very good students in this domain. Not only CMERI, NIT, IIT, all are lacking. So I will request the youngsters to take up these things, these topics as a career and come forward, because nowadays there are lots of opportunity has been given, and until and unless we do research in this field, there is no advancement. Because there are numbers of fields we have to work on robotics, on AI, so that human lives are less threatened in some of the area where human life of our operators should not be threatened. There only we will use robotics, AI, etc. So I request all of you to collaborate and to think and take a career in this means in this direction. That's the main motto of my today's lecture. Okay, thank you for your presence here.
Because we have already crossed the time, so we can take up one or two questions from the participant side. If you have any query.
Sir, thank you, sir, for delivering this nice lecture. Even though we are not from this field, I could understand each and every concept. Thank you. But I would like to ask one question, sir. Usually, in underwater, the LoRa protocol usually don't work properly for the robot to sense and move forward. The wireless protocols. Which is the best protocol to use for underwater aerial systems so that you can suggest?
Madam, this communication depends from environment to environment. Environment to environment. For open field, now just we are working with one project with Coal India, where we have multiple sensors at an open field, and there we are using LoRa communication. But in other case, for example, when we have tested one of our mobile robot in Damodar River, when we tested that time in previous time in say 2008, we tested one robot at our Damodar River. That time we used your normal wireless communication, 2.4 gigahertz. But it was rainy season. We found a very bad situation due to presence of thunderstorm or say charged cloud. But the same communication, when we went to underground mine, there was a structured environment and reflection from the walls, mostly stones. There that communication worked fine. But there LoRa communication failed. So this communication depends upon your location to location. Even as I told you, wireless communication in metal pipe, basically in boiler was a catastrophic loss. We didn't understand why it was not working. Later on we find out that it was due to this electromagnetic shielding. So this communication depends upon the area where you are going to work. It's dependent on. But in some cases for long range communication, this LoRa is fine for your this outdoor application. In inside communication, we have preferred this 2.4 gigahertz, this open band channel communication, that is fine. And so it depends upon where you are going to apply.
Path selection strategies. So you have discussed so many path strategies. So which is the best one, sir, among that? Because multiple you have discussed the path selection strategies for
Path again, what is means this depends.
like in underwater, sir, underwater communication.
Underwater communication, we prefer autonomous system. Means autonomous mode is there, and most of the times either A-star or this potential field method we have used. Okay, but nowadays we are using a different one. Means this reinforcement learning type of things robots are being used, because there are little bit means that dependence upon that particular deterministic model is little bit away. So that's why we will get a faster response time.
Thank you very much. We cannot take up any more questions now. I thank you, Honorable Speaker, Dr. Peter Day, for this insightful discussion on mobile robots. I think our participants will be benefited from this. Thank you.